For this lecture, we're going to talk about microcontrollers and what are microcontrollers and how can we use them and how do we select what a good microcontroller is. First, let's talk a little bit about some history. Before computers, electrical engineers used analog circuits to do things like control the attitudes of rockets and things like that. But during World War II, researchers invented machines that used digital logic that allowed computation. That was basically used for breaking codes and things like that. Vacuum tubes were used to set the zeros and ones on the computer. In 1948, the transistor was invented, and the transistor took something that was about the size, a couple inches in size, and shrunk it down to, a very small volume. So it's just a couple millimeters at most in size. That allowed vacuum tubes to be replaced and computers to shrink. In the late 1960s, microprocessors were born from integrated circuits. And in 1975, Bill Gates and Paul Allen made the basic programming language on the Altair computer, and that sort of allowed an explosion of computer use. They formed Microsoft that year. And in 1977, Steve Jobs and Stephen Wozniak made the Apple II computer. These are what those two computers look like. This is the Altair computer here. And then this Apple II computer here. I had something that looked almost exactly like this when I was in middle school. And you can see that there are disk drives here. Computers have grown up a fair bit. Okay, so what is a microcontroller? Simplistically, a microcontroller is a central processing unit on a single chip. All computers have a CPU. Those are the main brains of the computer. And it's sort of quite analogous to a real brain in that your brain does a lot of processing. But, it's subtly different in that your brain also holds all of your memories, but a central processing unit doesn't necessarily hold memory. There are central processing units that have memory in them, but we'll get into that in a little while. Everything else around the microcontroller, is pretty much a peripheral, which basically means that it allows input and output. And then the CPU, the central processing unit, does the computation. Just like you have eyes, you have ears, you have nose, you have mouth, and all of those allow input, and then your brain does computation on that. It's very similar to a computer. A microcontroller is really not super useful as just a simple CPU alone, and so oftentimes it is shipped with a central processor and then a bunch of other stuff that goes with it, and so that makes it sort of like a mini computer. They're shipped with memory, power regulation, and easy ways of doing input and output. There are thousands and thousands of microcontrollers, microprocessors. There's a huge range in functionality. Some are extremely simple and some are very, very sophisticated. So, for example, my old phone was a Nexus 6P, and it had 4 ARM Cortex-A57 cores running at 1.95 gigahertz. That means that it can do basically 1.95 billion computations per second on each core, and there are 4 cores. So ARM stands for Advanced RISC Machines, and RISC stands for Reduced Instruction Set Computer. So this is all sort of confusing lingo stuff, but that's sort of like when you see ARM. A lot of processors will be ARM processors or RISC processors. Anyways, details. A Raspberry Pi has a 1.2 gigahertz quad-core ARM Cortex-A53 processor, so it's a little less powerful than my old cell phone. The Arduino Nano, we're sort of using something similar to that, has an Atmega 328 processor, which is 16 megahertz. Pay attention to the 16 megahertz as opposed to the 1.95 gigahertz. So the megahertz is 1,000 times slower than the gigahertz. So this computer, the Nano, or the Arduino that we're going to use, is really, really slow compared to like a modern day cell phone. But, the Arduino Nano is $5, while, your cell phone costs $600 or something crazy. There's very different quality there. Let's keep going. So where do you find microcontrollers or microprocessors? I'm going to use those words sort of interchangeably because they can be used interchangeably. The short answer is that we find microcontrollers everywhere. In cars, they're in your radio, they're in the GPS, they're in anti-lock brakes, they're in the traction control system, they're in the display, they're everywhere in your car. Computers basically make the car now. When you push on your accelerator now, it used to be that you have a wire that goes from your accelerator directly to the gas. And so as you push down, it would literally move a lever and allow more gas into the engine. Now you basically push down and it sends a signal to the computer, and the computer says like, okay, I think that they want more gas. So then that opens up the gas in the car more. And you have a lot of balance between like oxygen and fuel and stuff, and so the computer takes care of all of that stuff. And it's all like literally under the hood. But it is a computer that does all of that stuff now. Same with just about everything in your car. Everything is controlled by microcontrollers now. Cell phones obviously have microcontrollers. There are microcontrollers in appliances, in clocks, in watches. In this camera that I'm using, there's obviously a microcontroller. Furnaces, temperature controllers, garage door openers, everywhere. They're everywhere. Why are there so many different types? Why don't we just have one type of microcontroller and then, that's it? Well, where it really comes down to is a balance between lots of different things. A light bulb doesn't need the computational power that your cell phone needs. And so putting a microcontroller like an ARM Cortex whatever in your light bulb will make it like a $200 light bulb or a $500 light bulb. You don't need that. So what you really want is you want a microcontroller that is very lightweight, doesn't use very much power, and costs like a nickel. And so, you basically want to balance the processor speed, the memory, the number of input-output pins, and then the cost in terms of dollars. And so, you do that cost-benefit analysis and you pick out your microcontroller based on that. Basically, processor speed for a microcontroller comes down to like roughly how many megahertz or gigahertz or whatever that it uses. That's a rough estimation. So you can actually go to this link or just do a Google search on processor speeds, and you'll see that like a 1 gigahertz processor may be a little bit faster than like a 1.2 gigahertz processor. It all depends on like how they're programmed and everything. But like a 1 gigahertz processor is going to be significantly faster than like a 1 megahertz processor because there's 1,000-time differential there. You can really pick out the different speeds of the processors that you really want. But once you get into like really close speeds, then you may actually have to do a lot more digging around. There are different types of memory in a microcontroller. Yeah, memory is where you store your code that you write and where you store data that you create on your microcontroller. Different types of memory have different capabilities and stuff like that. And so you basically have to balance like how much memory you need for storage of code and storage of data. Basically, the whole function of a microcontroller is to take input, do something with it, and then create output. In Engine 100, we're basically going to take sensor data and we're going to write it out to like an SD card. And so you take that data, you do some manipulation with it, and you write it out to an SD card. You'll take your SD card and put it in your laptop or something, and then you'll read that data. Other things like on a car, you press on the accelerator and the microcontroller reads like, okay, they want more power. And so then it sends some signal to the to the gas intake valves and opens them up more. And so you get more gas flowing into the engine. So it's inputs and outputs. And there's a question of like, how much stuff do you actually want on to take into your microcontroller? Do you need a lot of things going into your microcontroller, or do you just need a couple things going in? And some microcontrollers let a huge amount of information in, and some just a very small amount. You've probably heard of this thing called a GPU, which is a general processing unit. You find these in graphics cards a lot. The fundamental difference between a central processing unit and a general processing unit, they're very similar to each other, except a general processing unit, basically it has very, very small amounts of memory associated with it, but it does stuff with that very small amount of memory very, very, very quickly. And so it does linear operations on a tiny amount of data, which is basically like ray tracing for 3D rendering and stuff like that. So in a graphics card, you really want very fast 3D rendering. So for example, an NVIDIA GeForce GTX 1080 has 2,560 cores. Like a lot of cores, a lot of processors. But each of those processors have just a tiny, tiny, tiny bit of memory. So each of these processors can't like operate Word or anything like that. They can't do normal computer stuff. All they can do is like a little bit of array manipulation or a little bit of ray tracing or whatever. And they do that stuff very, very quickly. But like you can't use that on your main computer. You can only use it for graphic stuff. All right, I/O, input output. So there are two types of inputs and outputs. One is digital. Digital is basically the ones and zeros inside of a computer. And so there's a lot of input output that is digital in form, and we're going to deal with some of that in class. And then there's also analog. Analog is basically you read it as a voltage between 0 and some reference voltage. So for the Arduino, it's usually either 5 volts or 3.3 volts. And you could have any value between like 0 and 5 volts or 0 and 3.3 volts. That is very different than the distinct values of digital inputs. We're going to be doing a lot of analog inputs. Some microcontrollers have analog input pins, so it allows you to have that basically infinite number of positions between like 0 and 5 volts or 0 and 3.3 volts, but that's not really true. What you need in the middle there is an analog to digital converter, because the computer itself can't actually deal with like an infinite number of things. It needs to convert everything to digital. And so that's what an analog to digital converter actually does. And we're going to learn about those in class. Digital is basically how things work nowadays. We're going to learn a lot about analog inputs in class. You're going to use mostly analog inputs, but we're going to do some digital inputs in class too. It used to be that there was a lot of argument about like what type of digital inputs were best, and there is parallel and there's serial inputs, but really that all changed a while ago, and serial is really the way that the world has moved towards. And serial is like USB. USB stands for Universal Serial Bus. You all know about USB, I would imagine, because like your computer has USB, you plug stuff into the side of it, and those are USB ports. And that's basically how your computer reads stuff from the world now. Ethernet is actually like Wi-Fi is technically Ethernet, which is also a serial interface, which is interesting. There are other serial interfaces called like SPI and I2C. Almost all interfaces that we know about and talk about are serial interfaces. Let's say that you have a satellite. What type of inputs might you actually have? Well, you have lots and lots and lots of inputs. You have science data from the instruments. You have position and orientation of the satellite. You have temperature data from a wide variety of locations on the satellite. So for example, batteries are extremely sensitive to temperature, and so you sort of want to monitor the temperature all of the time. Solar panels are also very temperature dependent, so you want to know like what the temperature of the solar panels are. You want to know what the voltages and the currents from different systems are. So there could be hundreds of inputs that the satellite actually wants to know about. How does a microcontroller actually handle all of those inputs? If a system has a small number of inputs, then each input can get a dedicated line. So we can basically hook up every sensor to an individual line and then just read those sensors. If we have more and more and more inputs, we could either buy a processor with more and more input lines, which becomes very expensive, or what we can do is have multiple inputs on the same line. So for example, instead of using the analog to digital converter on the inside of something like an Arduino Nano, we can buy an analog to digital converter which has like 8 input pins, and then it will convert all of those, and then we basically just need one line to talk to that analog to digital converter, and then we can just query that and say like, give me the voltage on like line 1, give me the voltage on line 4, etc. And so you basically take 8 inputs and turn them into one input. So that works much better. If you have a lot of inputs, you can put them onto analog to digital converters. Let's say that you have way too many inputs. What you can do is you can use something called addressing. So basically you can assign like a temperature sensor an address, and then you can say, give me your temperature sensor number 47, and it will report its temperature. And then you can say, give me a temperature number 32, and it will give you the temperature reading. Addressing is a way that you can expand the number of sensors significantly. It requires more software, and it's a little bit more complicated to do in hardware, but it's one way of allowing a huge number of inputs instead of just a very small number. A microcontroller is very similar to your computer in that it has a central processor in it, and you run code on that. Write a program, you upload that program to your microcontroller, and then it does something with that. Microcontrollers are not like your computer in that they don't have a monitor, a mouse, a nice graphical interface. You don't run Windows on your microcontroller or anything like that. And so you basically have an interface on your computer where you can write code. You write that code, and then you click like an upload button. The interface device basically compiles that code, and it sends it over to the microcontroller. It's often very difficult to debug on a microcontroller because there's no like outputs. There's no like screen which says like, oh, you have an error. It just doesn't do the thing that you want it to do. And then you have to figure out how to do that or how to debug that problem. And so there's a lot of tricks to figuring that out. And we'll probably talk about that a lot more through this semester. On a microcontroller, you usually have 2 different types of operating systems. They operate in 2 different types of ways. One is like a looping way, where when you turn on the microcontroller, you basically have 2 functions that it runs. The first function is initialize. So you turn it on, it runs the initialize function, and then it basically does whatever you want it to do once. After it goes through the initialize function, it goes into this loop function. And the loop function is run over and over and over and over and over again. Just continuously run over and over again. So it goes through the loop function and then immediately goes back into the loop function, goes through it, goes back into the loop function, goes through it, goes back into the loop function. And so it just does the same thing over and over and over again. And that's really the type of operating system that we're going to use on the Arduino for this class. The other type of operating system on a microcontroller is what's called a real-time operating system. And a real-time operating system is like what your cell phone uses. And that is what's called interrupt-driven. And so your cell phone will basically sit there and do nothing. It doesn't ever do nothing. But it basically sits there and does stuff until it gets a signal, like until you pick it up and then it detects that the accelerometer reads some sort of thing, and then it tells you the time, and then you can click on the power button or whatever, and then it's like, oh, okay, so you want to like unlock the screen. And so it turns on the camera and starts looking around for your face, or does your thumbprint reader, etc. And so what basically is happening is it's being triggered by all of these different inputs. So like when you get a cell phone call, your cell phone recognizes that and it says, oh, something's happening. And then it goes into a function which responds to that something. And so that's why it's called a real-time operating system, because it's always sitting there waiting for real-time inputs. And then once it gets some sort of an input, it interrupts whatever it's doing. So if I'm listening to a podcast or Pandora or whatever, and I get a cell phone call, then it interrupts everything, and then it starts doing the cell phone function, and it actually lets me talk on the phone or whatever. So it's all sort of interrupt driven. Those are the two type of systems: looping, doing the same thing over and over and over again, and real time, which is interrupt driven. So the microcontroller in this class, typically we would talk about the Arduino Nano, but we're actually going to use a different processor for this particular class. We're going to use the Arduino 33BLE. It's not super capable, but it's really easy to use. So it is going to be a processor that is 64 megahertz. So that is significantly slower than your phone or whatever, but you're not going to need a lot of processing power for this class, so that doesn't really matter. It has a USB plug, which you're going to plug into your computer and interface with it. It is 3.3 volts, which will matter at some point in class, but it's okay. It has a bunch of memory, or a tiny bit of memory, not a bunch of memory. It has a tiny bit of memory which can be used for programming, and then it has a bunch of memory for like storing data and everything. We're probably not going to use this 1 megabyte of flash memory, but you know, it's there if you need it. It will be mounted on a breadboard, which is what we're going to use for the class. We'll go into breadboards and stuff later. It's around 20 bucks, which is really fantastic. That's one of the main reasons why we got it, because it's really cheap. It's really cheap, really easy to use. It uses C-like code, and so you're going to learn C in Engine 100 or 101, and so like it's consistent with what you're going to learn there somewhat. It doesn't use much power at all, and so you can actually run it off of a battery for many hours, which is really fantastic. All right, so what we talked about today was that there are lots and lots and lots of microprocessors available, and basically you can scale the type of microprocessor that you can use, that you want to use, on this problem that you need to solve. So for this class, we're going to do a few inputs and a few outputs, and so we don't need like a really heavy-duty processor. We don't need like a $200 ARM Cortex whatever processor. We just need a very simple thing like an Arduino. There are many considerations when you're thinking about microprocessors, such as like the processing power that you need, which for this class is not very much, the number of I/O pins, input-output pins that you need, the energy used, and so, you know, how much time will it take to use up the battery and everything. Cost is often a major consideration. You don't want to spend too much money on a processor, buying a really bulky processor when you don't need it, so you try to minimize the cost. And then the software development environment is also critical. Like, how complicated is it to actually program your microprocessor, microcontroller. So hopefully this video actually taught you a little bit about microcontrollers. Thanks for watching.